So what we're going to begin now is chapter 4, which is all about integration. So we spent a lot of time going through the process of differentiating. What we want to do is undo that process. So anti-differentiation is the section we're going to go over. It reverses the process that we've spent so long doing. So for example, if we have the function f of x equals x squared, we know how to take the derivative. It's just power rule, so it's 2x. So what we can say is x squared is the antiderivative of 2x, because if you start here and undo the process of differentiation, you get this original function x squared. Okay? So the antiderivative is going to be a set of functions, which we're going to use capital F of x plus c, so that when you differentiate f of x plus c, you land exactly back to the function you started with. So this is really nice because when we find the antiderivative, we're going to be able to check our process by differentiating, and you should land exactly where you started at, because these processes just undo each other. So this value of c is called a constant of integration, and the reason we're always going to add it at the end is because when you take the derivative of c, it's always going to be 0. So it's going to lead into the most general antiderivative we can possibly have. So we have another way to actually write this, which is going to include something called an integral. So that's this whole section or whole chapter we're working with. So if we want to undo the antiderivative, we know we have that operator d over dx to talk about differentiation. We have the prime notation to say take a derivative. This operator is going to undo that integration and tell us to take an antiderivative. So it's going to be a specific symbol, and it's going to look like an S. It's an integral sign. So we want to undo the differentiation of this function to get this capital F of x, which is the antiderivative. So each of these pieces has a different name. This S-looking symbol is called the integral. The function that goes on the inside is called the integrand, and that dx kind of comes from where those differentials we learned. It really is going to help us with what the variable of the integration is. So the reason we use this looking S is because it's like a sum, and you're going to see how we relate it to areas in the next section. So the expression that's on the left-hand side is going to be an indefinite integral. So you have nothing going on out here. It's an indefinite thing. In the next couple sections, we're going to add bounds to start the integral somewhere and the integral elsewhere. So that will be what we call a definite integral. So let's get some practice with antidifferentiation. We're going to determine the indefinite integral. So that is, we want to find the antiderivative of each integrand, or the function inside. So we're going to start by finding the antiderivative of 7 with respect to x. So what we need is a function whose derivative is 7. So if you think back to all these differentiation rules I learned, if you had any type of line, 3x, the derivative is 3, 8x, the derivative is 8. So the integral of 7x dx, or 7 dx, is 7 times x plus c. And so the way we can actually check our answers is, let's take the derivative of what we said the antiderivative was. When you differentiate 7x, it's 7. When you differentiate c, it's just a constant, it's 0. We land with exactly the same function back that we have in the integrand. So we found the antiderivative correctly. Okay, let's try another one. Let's take the integral of 4x to the third with respect to x. So I need a function whose derivative is 4x cubed. So if we think of reversing that power rule, if you take the derivative of x squared, it's 2x. X cubed, it's 3x squared. X to the fourth, it's 4x cubed. So we're losing that power when we take the derivative. So if we're undoing it, we're going to increase the power. So let's try x to the fourth plus c. Check our answer. The derivative of x to the fourth plus c. Derivative of x to the fourth is 4x cubed plus 0. So this is exactly what we have inside of our integral. So we found the correct antiderivative. Okay. And then finally, let's look at the integral of e to the x dx. The only function whose derivative is e to the x is exactly itself back. So we can check our answer. Let's differentiate e to the x plus c. Derivative of e to the x is e to the x. So we're good. So this is a great thing. We can always check our answer by differentiating what we got in the end. The derivative of this better be exactly what you have in the integral, because the integral and differentiation will undo each other. Okay? So because we have nice rules for differentiation, we're going to have nice rules for anti-differentiation as well. So the first one is when you start with the integral of a constant, the antiderivative will be the constant times x, because the derivative of kx is just going to be k. And then we always want to tack on this plus c at the end. If we want to integrate x to the n, this is reversing that power rule. So you lose a power when you differentiate. So when we integrate, you've got to gain a power back. So if I have x to the n, we're going to increase the power by 1 and divide by the new power. So it's very similar when we took the derivative of x to the n. You brought the power down, decreased the power by 1. You bring the power up. Before it was multiplication, so now it's going to be division. Okay? So this reverses our power rule. The only problem is when n is equal to 1, because that will make us divide by 0. Because really, that particular case deals with our natural log function. If n is negative 1, that's just 1 over x. The only function whose derivative is 1 over x is the natural log. We had to be a little bit careful and put these absolute values because the natural log function has a domain where the inside is strictly positive. But 1 over x doesn't have restrictions. I could plug negative 2 into it, no problem, and the function is defined. But it's not going to work over here. So that's why we need these absolute values to guarantee that our derivative or our domain is correct. And then finally, if we have an exponential function, the derivative of e to the ax is going to be itself, but you would get an extra a that pops out from chain rule. So instead, when I integrate, I'm going to have to divide by that value of a, because the derivative of e to the ax will be a e to the ex, so the a's will cancel. Okay. So these are our most general antiderivatives. So let's go ahead and just do a bunch of problems. Let's find the following indefinite integrals. We want to integrate x to the 6. That's reversing our power rule. So you increase the power by 1 to 7, divide by the new power, plus c. So we can check our answer by differentiating what we got. Derivative of 1 over 7 x to the 7, you bring the power down, decrease it by 1, you get exactly x to the 6 back. So we get what we started with. Okay. Now if we want to go through the integral of the square root of x, that really is just a power, remember, it's x to the 1/2. So what we do is we increase the power by 1. 1/2 plus 1 is 3/2. And then you have to divide by the new power, and then you need your plus c at the end. So dividing by 3/2 is the same thing as multiplying by 2/3. So this is our most general antiderivative. So let's go ahead and check by differentiating the antiderivative. Derivative of x to the 3/2 is you bring the 3/2 down, becomes 1/2. So everything cancels out nicely. And you just get x to the 1/2. So now we have some properties of anti-differentiation, just like we had some properties of differentiating. First one is when you take a derivative, the constant stays attached. Same thing's going to hold true for the antiderivative. The c can pop out. You can take the antiderivative of what's inside. Differentiation splits across addition and subtraction, so integration is going to do the same thing. The one thing we can't do, though, is if you have the integral of the product of two functions, it's not going to be the same as the integral of each separately. So you can't do this, because you can't do that with derivatives either. You have to apply the product rule. So if you do end up taking more math classes at some point, you'll learn a procedure to reverse power rule, but for now, we're not going to get through it because it's a little more complicated. So let's go ahead and evaluate a couple different antiderivatives. First one we're going to go through, I'm going to add more steps than you need to, but just while you're getting in a process, feel free to go through this. So I've got two different functions that are being added together, so we can write it as the integral of the first one minus the integral of the second. And then you can pop the constant out of each. So we can take out the 5, we can take out the 2, and find each antiderivative separately. So the antiderivative of x squared would be x cubed over 3. You multiply by the 5. Antiderivative of e to the 7x is still itself, but you have to divide by the 7. So this is going to be our most general antiderivative, 5 over 3, x to the third minus 2 over 7, e to the 7x plus c. And we can go ahead and check by differentiating. So the derivative of 5 over 3 x to the third would be 5x squared. And then for 2 over 7 e to the 7x, you get exactly it back, but chain rule tells you you have to multiply by the derivative of 7x, which is 7. So those cancel out nicely, and you do indeed land back with just 5x squared minus 2e to the 7x. Okay. So now let's try this one. Right now, it's not in a good form that I can't tell you what the antiderivative is. So we do have to do a little bit of algebra and FOIL it out. So x plus 4 squared is x squared plus 8x plus 16. Now I take the antiderivative of each. Antiderivative of x to the second, x to the third over 3. 8x would be 8x squared over 2. 16 gives you 16x, and then you get a plus c. And then we can simplify it just a little bit. The 8 over 2 reduces to 4. And then we can go ahead and check by differentiating. So you just apply power rule a bunch of times, and you do indeed land with the same thing back. Okay. So every single time so far, we've had this arbitrary value of c because it is the most general thing that is the antiderivative. But in some instances, we're going to actually be able to find the value if we know a point that our function has to go through. So the antiderivative gives really a family of curves because of the plus c. So for example, if you have f prime of x equals 3, then a general antiderivative is 3x plus c. However, all of these are also functions that are antiderivatives because they all satisfy that the derivative will be 3. They just have a different constant at the end. So it creates these family of curves that all have exactly the same derivative. But if I now add in an extra condition that f of 0 has to be 1, only one of these functions will go through 0, 1. So if you evaluate all of these at 0, just this function here will satisfy that particular condition. So we only get one solution. F of x has to be 3x plus 1. What we can do, however, is we can actually find that function using the most general antiderivative. So the derivative is 3. The most general antiderivative is 3x plus c. Now what we'll do is we'll use the initial condition. F of 0, if we plug that in, will be 3 times 0 plus c, which is just c. This has to have an output of 1. So this thing better equal 1 from this condition. So that immediately tells us c must equal 1. So the function that satisfies this condition is f of x equals 3x plus 1. Okay. So you don't want to have to sit there and try to go through every possible combination to find the value of c. Instead, use it algebraically to find the quantity you're looking for. So let's try just 2 examples. Let's find a function such that the derivative is x minus 5, but it goes through the point 1, 6. So the first thing I want to do is I want to find the most general antiderivative. So I want to integrate the derivative, which means I'm going to integrate x minus 5. Antiderivative of x is x squared over 2. Antiderivative of negative 5 is negative 5x. And then we get that arbitrary plus c tacked on. Now I want to utilize this condition to find the value for c. So if we plug in 1, we'll get 1/2 minus 5 plus c, which if you do 1/2 minus 5, it's negative 9 over 2. Well, when you plug in 1, you better get 6 as an output, so negative 9 over 2 plus c better equal 6. Solving for c, we end up that it's 21 over 2. So the only function that will go through this specific point is 1/2 x squared minus 5x plus 21 over 2. Okay. So let's try one more. We've got the derivative is 6x squared minus 4x plus 2, and it needs to go through the point 1, 9. First thing, let's find the most general function. So we're going to integrate our derivative. Antiderivative of 6x squared, 6x cubed over 3. Antiderivative of negative 4x is you increase the power by 1, so you get 4x squared over 2. Antiderivative of 2 is 2x, and then we get our plus c tacked on. So we can clean up those numbers. 6 over 3 is 2, 4 over 2 is also 2, so this becomes our most general antiderivative. So now we'll use this condition, we'll plug in 1 and see what we get. So that'll give us 2 minus 2 plus 2 plus c. This will be 2 plus c. And it better equal 9, so that tells us 2c plus 9, or 2 plus c is 9, so c has to equal 7. So the only function that satisfies the derivative being 6x squared minus 4x plus 2 and goes through the point 1, 9 is this particular function, 2x cubed minus 2x squared plus 2x plus 7.